Good afternoon, everybody. Hope you're all healthy and safe at home. Let us continue with our Module 3, Chapter 4 on bounded linear operators. So, in the previous class, we had studied about what is meant by a bounded linear operator, and we had done a theorem related to that. In this lecture, we shall discuss about the concept of compact operators. Now, let's see the definition of a compact operator. A linear operator A from x to y is said to be compact if for every bounded sequence xn in x, the sequence A of xn has a Cauchy subsequence. Okay, we know the definition of compactness. We have learned it in topology and all. So when we talk about compact operators, the definition is as follows. That is, for any bounded sequence in space x, the sequence A of xn should have a Cauchy subsequence. So this is a definition of a compact operator. Now you can note one thing which is simple to prove, that a fact about the compact operators is that a compact operator will always be bounded. So let's see how we can show that. We all know that how can to prove that an operator is bounded, we must show that norm of A must be here. If we are taking the operator to be A, norm of A must be less than some finite value. So how can we show that? Let us consider let A be any bounded a compact operator. Okay, let A from x to y be a compact operator. Now we are going to show that this is bounded. Okay, so how can we show that? First, let me suppose consider an open ball, consider a unit ball, okay, a ball of radius 1 in the space x. Okay, then clearly it is bounded, right? It is clearly bounded. So if possible, suppose that the image of this unit ball, okay, if possible, suppose that the image of this unit ball is unbounded. Okay, for an operator to be bounded, this image must also be bounded, right? So if at all this is unbounded, then what happens is, then we can easily, I just want you to imagine this, okay, then we can find a sequence xn in the space in the unit ball in x. Okay, we can find a sequence xn in the unit ball in the space x, such that what will happen, as A of xn, that is the image, is unbounded, we can find a sequence xn such that A of xn is going infinitely. That is, the norm of A of xn is unbounded, because if we are assuming that it is possible that the image of this particular unit ball, we have a unit ball, the corresponding image is unbounded, so we can always find a sequence such that norm of A of xn is tending to infinity, or it is not it is not bounded by a particular value. So this will bring a contradiction to the fact that A is a compact operator. Why? If A of xn tends to infinity, then we cannot find A of xn cannot have a subsequence. Okay, cannot have a Cauchy subsequence. We cannot find a subsequence of A of xn which is Cauchy. So this is a contradiction to the fact that A is a compact operator, because corresponding to any sequence xn in x, A of xn must have a Cauchy subsequence. So this contradicts the fact. So this assumption that the image is unbounded is false. So that means if we consider any unit ball in x, the corresponding image is also bounded. That is, unit ball is bounded, so corresponding to any bounded set, the compact operator gives us another, the image corresponding to the compact operator will also be bounded. So we can that gives the proof of the note that a compact operator is always bounded. It will always remain bounded. It is direct from the fact of the or the definition of the operator and the definition of boundedness. So I hope the proof is clear. So next, to understand the concept of compact operators, we must first discuss the concept of compact sets. Okay, here so we are coming down to we are not discussing about operators now. We are coming down to the concept of sets. So let's see the definition. A set K, which is a subset of X, is said to be compact if and only if every sequence xn in K, there exists an element in K, x in K, and a subsequence xni of xn such that xni converges to x. Okay, or to be more clearer, you can just say that a set K, which is a subset of a space, subset of another set X, is said to be compact set if for every sequence we can find a convergent subsequence. So that is what is the definition of a compact set. Now we will introduce another term called relatively compact set. A set K is said to be relatively compact, or it is also called as pre-compact, if every sequence xn in K has a Cauchy subsequence xni. Okay, so compactness means corresponding to every sequence we have a convergent subsequence, and relatively compact means corresponding to every sequence in K it will have a Cauchy subsequence. So that is the definition of relatively compactness. Now there is another note which I would like you guys to work on it. That is, if X is compact and K is a subset of X which is relatively compact, then we can easily show that K closure is also compact. So just work on this note. We shall discuss it in later classes. So this is what you have to prove, that is if we have a relatively compact subset, then its closure will always be compact. So that's it. With this we shall wind up today's session. Thank you. Stay home and stay safe.